monthly webinar series. And by way of introduction, for those of you not familiar with UVIG, we're a membership-based nonprofit organization providing our members with good information and resources for renewable energy decision-making, peer-to-peer networking, knowledge sharing, and professional education experiences. We just finished our fall technical workshop in Nashville, which I hope some of you were at, and our next activity is going to be the spring technical workshop in Tucson, which you're all invited to attend. There's really nothing else quite like UVIG anywhere, and if you're new to UVIG, I strongly encourage you to follow up with us if you like what you hear, and I don't think you'll be sorry if you do. Okay, so just a few logistical matters before we get started. The phones are muted. Right now, Jonathan O'Sullivan, the presenter, is available for speaking. I'm available for speaking, and Margaret, who is the administrator of the webinar, is available for speaking. But otherwise, the phones will be muted, and we'll ask you to use the question and answer box to submit your questions, and we're trying to save 10 or 15 minutes at the end of the webinar for Q&A and discussion with Jono, and plan to wrap it up at the top of the hour and respect everybody's time commitments. So let me go ahead and introduce our webinar presenter, Jonathan O'Sullivan, Manager of Innovation at AirGrid, which is the transmission system operator in Ireland and Northern Ireland. Jono drives a number of specific technology strategies in his position there, and among them is the development of the DS3 program, which I'm sure many of you have heard about, delivering a secure, sustainable power system. And it really covers the secure and reliable operation of the Irish power system with pretty unprecedented levels of wind electricity by 2020, which Jono will go into in more detail. It covers the technical, economic, and government policy considerations. John's been in the industry for about 20 years, working in planning, operations, market design, and in recent years, he's been central to the implementation of the first electricity market in Ireland in 2000 and the first all-island market in 2007. Jonathan is an active member of ENSOE, the European Association of Transmission System Operators. There he's on working groups and committees on markets and renewables and long-term market design, among other things. By the way, Jono is also a speaker at the European Markets Design Workshop, which we held with EnergyNet.dk in Denmark earlier this year. Jono's been an active participant in UVIG for a number of years, good friend, and I'm pleased to introduce him to present this webinar on renewable energy and market design challenges. Okay, Jono.
Thanks, Charlie. Almost sounds like an introduction my mum wrote, but thanks very much. Folks, my name is John O'Sullivan. I'm Manager of Innovation in AirGrid. It covers a remit of a range of things that we're doing at a system level in Ireland. What I'll focus on at the early part of the talk is how we're managing wind integration. But towards the end of the talk, I want to broaden it about how we are now thinking about how we are managing a range of other disruptions that are going to happen, transformations on power systems in Ireland anyway, by probably 2030. So that's where the beyond comes in. And what I'm really going to try and go is, I genuinely believe what we're doing here in Ireland and Northern Ireland is relevant to other power systems where the policy ambitions are similarly ambitious. And to the extent I can make that argument, that's where I'd love the questions to come from. But I start from a position of I have to make a confession. The first thing is I'm a power system engineer, which means that I think that the three-phase AC power system is probably the greatest invention ever. And Tesla kicked the proverbial backside of Edison back in effectively between 1882 and 1896. AC basically triumphed over DC. But worse than being a power system engineer, I think I understand economics. I'm an enginomicist, which makes me delusional or dangerous, or probably a combination of both. And fundamentally, why I believe in markets, I think we have designed our markets to deliver something the consumer doesn't want. And because of that, the incentives and the direction of investment is all wrong. And unless we recognize that fundamental misguided nature of energy markets, we're not going to get to those policy ambitions irrespective of the evolution of technologies. That's essentially the talk, and hopefully over about 20 slides or so I can make that argument why the market needs to change philosophically, practically, how might you do it and how we're doing it in Ireland, and how that might actually help whether it's Europe or the United States of America in the context of trying to deliver on similarly ambitious targets. So where I get to really right now is that there's a range of forces at play that are really driving transformation on electricity power systems globally at the moment. I think climate change is a big issue. It's certainly a big issue for Europe, and it's a big issue around the world, notwithstanding necessarily America's suggesting they're coming out of the agreement. But they're not necessarily saying they're not trying to achieve it, they just want better terms. I personally don't argue climate change because I think it's been politicized, and I as an engineer and a scientist to a certain extent, I'm concerned about some of the things. But I do believe in climate change because I think if it took 65 million years to create the fossil fuels, and we're having a discussion in 150 years to 200 years of usage, we're at the halfway point. It's simply not a good husbandry of a very scarce capital resource. Energy security is something that is probably more relevant. I think it's very relevant for Europe and Ireland, less so for America, because America has a lot of its own indigenous resources and you have choices to make. But Europe currently imports more than 400 billion euros a year in imported fossil fuels, has an 80% dependency on imported fossil fuels, rising by 2035 to 95%. Ireland in 2000 had an import dependency on total energy usage of 95% of our energy was imported from outside Ireland. There was only one country with a higher energy security dependency, and that was Israel. And fundamentally, strategically, that sort of dependency on energy security drives a need for actually indigenous sources of energy, whether they be renewable or not, in my view, and I think Europe's certainly in that space. Tackle fuel poverty is a very important consideration, because a lot of the solutions people are talking about, say solar or wind or storage in homes, the first people who will be able to afford them are the rich. And the problem is, what's left is that the network which is left with less usage by the rich and more usage by the poor, does that mean that the poor are going to have to pay more for the existing grid? And that gets you into a political issue that you shouldn't underestimate. And so while any solution might be good in general, it won't work if it doesn't satisfy that political dimension. And then we've got on the far side probably two fundamental disruptors that are going on around the world at the moment. We have the Internet of Things, that basically means that things that were never conceivable 10 years ago are now not only possible but probable. And electrification in the rush to decarbonize, it's my view that three-phase AC power systems will be a dominant structure going forward into the future, and we might talk about microgrids later. 50, 60 years, and we're going to electrify heat and transport to various degrees. And that's fundamentally meaning that to meet any sort of targets of renewables, we're going to need more renewables on the power system and how you connect them, and more importantly, how you operate the system in that world really is relevant. Which goes to, why is Ireland, or the power system of Ireland and Northern Ireland, in any way relevant to this discussion? What does it do? Why? What I have up here is a map. The first thing I would know is a map. It was an Irishman who drew the map. Ireland is disproportionately greater size than France and Great Britain and all of these places. But what it really shows is, under European law in electricity, when you boil down the various commitments by countries to meet renewable electricity targets by 2020, which they're only European-wide targets for 2030, which I won't get into. What you see is that many countries have very large renewable targets. Sweden is 63%, Austria is 71% of its electricity coming from renewables by 2020. However, when you look at Austria and Sweden, a lot of the colour there is the beige colour, and that's coming from known hydro-synchronous resources. Fundamentally, the water hydro capability of Europe is maxed out, and we're not going to get any more renewables from them, or not material. But when you look at Ireland, and we're doing 40% of electricity coming from renewables by 2020, 37% of it is coming from wind, which is effectively a new form of technology. And when you new form of technology like solar or wind, and more importantly, if you look at the synchronous areas from a power system, the synchronous areas, the island of Ireland, the island of Great Britain, the continental Europe and Scandinavia, they're fundamentally different systems from a power system perspective. And when you look at those systems and look at the relative penetration of the new technologies, non-synchronous variable technologies by 2020, Ireland and Northern Ireland power system is effectively 10 to 15 years ahead of what other systems are likely to achieve or trying to achieve. But more importantly, when you look at this, this is an average, not a peak. So it's my view that too much analysis previously been done on considering about average of the energy. But when you think about it, wind sometimes blows, sometimes it doesn't. And sunshine shines, sometimes it doesn't. And the real issue is, if you're to average 37%, at times we're going to have to meet a power system coming solely from wind and solar of much greater than that level to make any sort of effective use of the wind that we're going to install. And when we looked at that, and that was probably the first thing, we significantly looked at that issue between 2008 and 2010 on the Ireland power system. So we went out to 2020 and did a study with the levels of wind that we thought we needed. And we did that study in a real technical manner. Now, what you got in that set of studies, which is this graph, it's almost like the flag of France with the wrong colors, but green, amber, and red. And what we see on this graph is we studied from a minimum of 3,000 megawatts of load on the Irish and Northern Ireland power system, up to 8,000 megawatts of load, and from 0 megawatts of wind up to 8,000 megawatts of wind. And we did about 500,000 different snapshots of the power system, did a range of different studies from low flow, short circuit analysis, transient stability, short circuits, small signal analysis. And what we effectively found out from our modeling up at this sort of level is that up to 50% of our power system coming in real time from this sources was stable. We didn't have to do anything. Now that's a very important statement, because in 2002 in Ireland, EirGrid, or its precursor, ESB National Grid, put out a wind moratorium and says, we can't connect more than 400 megawatts of wind to the power system because we don't think it will work. Now, in 2007, we got a new CEO in with a director of operations who's now the CEO of the organization, said, no, we're going to try and facilitate renewables, and basically got this set of studies kicked off. And that set of studies basically said, actually, at 5,000 megawatts or 6,000 megawatts of load, you can manage up to 3,000 megawatts of wind securely on the power system. And to put that to test, we had a storm yesterday, Storm Ophelia. It's actually a hurricane, first one in living memory for me in Ireland. But we had a similar, but not quite a hurricane, about 3 years ago where we weren't even prepared for it, called Storm Darwin, where we were operating up about 2,500 megawatts of wind on a 5,500 megawatt system. We lost 72, 110 kV wood pole constructed lines. We lost 370,000 customers, but we didn't lose the system. And effectively, the first acid test of this policy up to 50% was found to be resilient. We didn't lose the system. But what we did find for the Ireland and Northern Ireland power system up to 2020, that if you wanted to go up to 75% in real time to make better effective use of your wind, you would have to do things that you aren't doing at the moment. New business practices, new business processes, things that you didn't really appreciate, and have to be basically break down an inherent bias that we're all based on. Our planning of power systems was based on diversity and synchronous generation, and our operation was based on those same principles, and you fundamentally have to change those principles. But if you do, you can get up to 75% in real time. For 2020, above 75% for the Ireland and Northern Ireland power system, we didn't think it would be prudent to operate. Now, if you tell me for 2030, can we, I'd say we might be able to. It's a separate discussion. But in the 2020 context, we said probably not. This is based on 2 years of extensive studies, which I can get into any which way level of detail that anyone wants to get into. But rather than get into any detail, the big thing is the so what for politicians. And the so what really goes like this. If you install the level of wind by 2020 and you only go to 50%, if you look at the 50% on the right-hand graph, that will mean that we're curtailing or not allowing run over 25% of the annual output of wind farms in order to maintain a resilient power system. However, if we manage to get that up to 75%, which we think is doable, that curtailment level will fall to about 5–6%. So to the politicians, the so what is, if you do nothing and do nothing of this program of work, you're simply not going to meet your targets, or you're going to meet them very expensively. You're going to have to install a way more wind than you thought to meet them. However, if you do a program of work to address these issues, and that program we call the DS3 program, we think you can manage to operate this power system up to 75% in real time in Ireland and Northern Ireland by 2020. And that will make an effective use of the wind that you're already thinking of installing to meet your public policy. That's the general study. Out of it, and this is very important, when you looked at a little bit more detail and did some high-level sums, when you looked at the 2010, the purple curve, and against the 2020, 8,700 hours in each of them, and asked what was the minimum of inertia in each half an hour, what we were seeing is that we would drop our inertia we would be operating about 20,000 megawatt seconds instead of a current minimum of about 25,000 megawatt seconds. And we would be operating about 30% of the hours below the lowest minimum inertia that we operate today. Simple question, is that going to be reliable? I'm not saying it is or isn't, but keep an idea of the shapes. Reactive power, a lot of people say reactive power is a local issue, but we were losing hour on hour about 25% of our total reactive capability on the power system that we've traditionally used. And that's an issue. Yes, you might say we're getting other reactive capability, but it wasn't matching like for like. And fundamentally, I would argue that sort of loss of total system reactive capability is a system issue, not a local issue. And we might have a chat about that. And this last one on ramping was basically we saw the uncertainty that we were going to have to manage on the power system from 1 hour ahead to 12 hours ahead to 24 hours ahead as fundamentally changing. So what we looked at in 2010, we basically looked at how much change do we have to deal with it in an hour's time or in 4 hours' time, and how much capability do we have in the system to deal with that. And that was the blue curve. And then when we went out to 2020 and asked the same question, what we saw is for every hour we looked at, we had a 20 to 30% increase in uncertainty that needed a ramping margin to effectively manage. So all I'm using for these, without getting into them, is that there were technical scarcities, but keep the shape of those curves in your head, because I'll come back to it. But we are effectively managing the power system today. These are curves taken from the Ireland power system only 3 weeks ago. We are up to regularly hitting 60% in real time of the system coming from effectively wind. And we're currently at about 30% of the annual output coming from wind, and we're moving up to 65% by the end of the year with the plan, the DS3 plan in place to address all the issues we need to address to get to 75% in real time by 2020. That includes new control center tools, it includes new business processes, it includes a whole range of things, and it includes a fundamental redesign of the energy market, which I'll get to. But for a market to work, ultimately you need two fundamental dimensions on it. You have a structure and you have a design. The structure really hangs around, have you enough competitive parties at play to come into this? And are you doing things that are inherently creating barriers for participants to come into this? I believe that there's an inherent bias in all energy markets that is implicitly assuming synchronous generation. While that bias remains in place, you are creating barriers for non-synchronous technology to be able to reasonably enter into the market. And it's only by addressing those structural issues will you be able to make it work. And on the design issue, I am saying that fundamentally what you pay for and how you design that needs to change. And at the moment, the design of the energy market is based and predicated on that people want energy, and therefore we have an energy market. And I would conjecture, in fact, you go stronger than a conjecture, I would state, people don't want energy, they want lifestyle. And so fundamentally, the design of energy markets as we know it, in my view, cannot deliver on the ambitious policy ambitions of renewables and demand-side participation at scale. But let me expand on that a little bit more. So in Ireland, we are definitely breaking down what I would say known barriers, which I won't focus on too much, but we had to get control of every wind farm, large wind farm that was coming on the system. When we started this, we had none. Now we have about 3,600 megawatts of wind. We have about 3,000 megawatts of it, very controlled from our control center today. We don't spend any much time doing forecasting ourselves, but we do buy the best-in-class wind forecast out there. We do have an online real-time dynamic assessment in the control centres, which I think is a bit novel, but to us it's known. It's about how we use it going forward. And we have a general enforcement of standards, so we're trying to create a level playing field across all players. And one part of that was there is a capability that people are supposed to meet in the current grid codes. They're simply not. A lot of the grid codes are self-certification, and I don't agree with that. So we've basically gone after systematically over, and it's taken 10 years to get, there's a credible threat of enforcement on standards now across all participants, whether they're commissioning, testing, or we will catch them in the act over the time. But I think a lot of these things are known, and other jurisdictions are also dealing with them. What I really want to focus on, in order to manage the levels of renewables that we're doing, we've also are looking at breaking down other barriers that I don't think are well understood. And in this case, that's really what gets you above the 50%. In Ireland's case, in Northern Ireland's case, one of the big issues, because we're going to have less inertia on, we're going to see much higher rates of change of frequency, rock-off events. Those rock-off events can inadvertently lead to tripping of distribution-connected generation, which have protection settings set at a level that, for loss of mains reasons, which are inappropriate. Also, can the generators withstand that rock-off capability? We believe they can, and we've recommended a move of the rate of change of frequency from 0.5 hertz up to 1 hertz per second as measured over 500 milliseconds. Now, on a larger system like the United States Western or Eastern Interconnect, I would say you wouldn't have a rock-off issue per se, but you would have a distributed inertia issue in that you might have pockets of inertia and pockets of non-synchronous generation, and you might have to worry about that. So rock-off may not be exactly the issue. I think distributed inertia will be an issue. Ramping is one that I would also say that we're very minded. While we only get best-in-class forecasting, fundamentally our philosophy is there's too much focus on forecasting as a solution to everything. What you actually have to do when you're becoming a weather-dependent system is to manage the uncertainty in a better way. And so I would say if I'm a great forecaster of wind, the technology or its tool sets that I develop for that may not be applicable to how I forecast solar, may not be applicable to how I forecast demand participation going forward. Yet all of those, as they become material parts of the power system, means that you have to manage variability and uncertainty in a different way. And so we've created a whole policy and incentive around how we manage ramping on our power system over the different hours, 1 hour to 12 hours. It's a sort of a no-regrets insurance policy. System voltage, I said we're down 25%, 50% in new wind farms in numbers. We have about 300 wind farms in the Northern Ireland power system. 280 of them are on or 250 of them are in the distribution network, and half the megawatts are in the distribution network. And so you're going to need reactive capability coming from the distribution network. And also a 25% reduction, it's a system-wide issue. It's not just a local issue, and you need to get into a whole range of things in that consideration. And the last one that is really important, that certainly when we started this, a lot of people were saying you add wind farms into a power system, they make them more stable. And I couldn't agree with that when I got into research. I said, yes, maybe at low levels, 10, 15, 20%. but not at high levels. You've fundamentally taken away all the synchronizing torque on the power system, the glue to keep the system together. And when we did our studies on this, and we did them blind, and then we put the results together, there was a beautiful, what we call a J-curve, which showed increasing stability up to 60%, but then a massive increase in unreliability past that, which basically said, look, above 70–75% on the Ireland, Northern Ireland power system, if you sneeze, the system will fall over. So fundamentally, the resilience that society has come to expect in the power system is fundamentally challenged if you just keep on adding in non-synchronous technology and displacing synchronous technology. Now, that's not to say that you can't go there, but you need to go there and realize that you have technical scarcities that you are creating, and you need to address those technical scarcities in order to maintain what the consumer actually wants, which is affordable energy delivered in a resilient way that they don't have to worry about what the hell's going on in the power system. And I would argue that those four things here at a high level are not being considered in energy markets around the world, and because they're not, and they're very pertinent to renewable integration at ambitious levels, then I think the markets fundamentally can't deliver in an effective manner. And behind all of this, we are trying to change our internal business process and practices and procedures and tools in order that we can manage all of these things and to take these services from a range of new technologies that we wouldn't normally take them from. So most TSOs at the moment only really take services from synchronous generators. Now, you have a twofold issue. As you displace the synchronous generators, you're losing your current source of resources, but you're also creating new issues that you didn't know because you never had so little synchronous generation, and you have to replace those two issues as well, which means not only you need to incentivize for it, you need to come in with the business practice to actually make sure you're not inherently or inadvertently creating barriers for those new technologies to come in and do it. And you must do this as a prudent TSO. So I can't have a blackout in the middle of it and learn afterwards. I have to make sure I get it right before I get there. But in all of that, even if I break down all those barriers, you have to basically come up with and acknowledge that the fundamental finance of the energy market is moving. And we have done a major thing in this that I'll try and explain. That, first of all, that if you look at where the market is today with a traditional market, a lot of the money is in the energy payments in the energy market. The variable cost, which is invariably paying down fossil fuels, probably is paid out of the energy market. Then anything above that is supernormal profit, which combined, if you have a capacity market, generally covers your capital costs. And on the upside, you have ancillary services, which are generally very small, generally change every year or two with the regulator. They're not investable, and they're what I call upside for the equity investor. So Warren Buffett doesn't lend money against ancillary services. He'll lend it for capacity payments and energy payments. And invariably what you get behind contracts is availability and efficiency payments or things in the OEM contracts. However, going forward, if we displace a lot of the fossil fuel with renewables, the size of the money in the energy market should reduce. It also becomes more variable, which becomes problematic or volatile. But our capital costs might increase because we're now installing a lot of wind and solar. And so while our variable costs might actually reduce, we have to get an increased capital cost. And in this one, I just happen to make them the same size. But ultimately what I'm saying is system services comes in not to be upside for the equity investor, but to be allowed to solve the technical scarcities in the future to facilitate public policy objectives and allow people to make investments in that capability today. So they move the money that they're getting from an energy market only to something that is more complementary and more of a hedge in system services. Those system services are designed exactly to cover the technical scarcities that you can see if you look out far enough with the renewable levels that the policymakers are asking. And we've effectively done a version of this complete redesign of system services in the Ireland and Northern Ireland energy market. And the interim arrangements are in place right now, and the enduring arrangements are due to go live in 1st of May 2018. And I'll try and explain high level what we're doing in that. The first thing is we've created a new set of products that actually go to meet some of the technical scarcities that we knew. So while the classic ancillary services is POR, SOR, TOR, primary operating, secondary, tertiary 1, tertiary 2, and replacing, we see increasingly the need for synchronous inertial response, fast frequency response, and fast post-fault active power recovery products. They're all less than 1 or 2 seconds or less. And we also see longer-term products, 1 to 24 hours, called ramping margin. So I'm saying we now have those products in our system services. And on top of that, we also have dynamic reactive power, which is a surrogate for synchronizing torque. And we also have a modified steady-state reactive. We also put in the context of how you build out the network, and the network there affects how much reactive you want. But ultimately, we've redefined some of our products. Instead of 7 now, we have 14. We've also come in with a major structure of how you get payment on this. Now, the argument we made, which the regulators broadly accepted, is the value of system services. The ancillary services in the Irish market were worth about 50 million a year, but we're only on a yearly tariff that the regulator reviewed every year. What we're proposing is that they're valued at 235 million, which is based on a cost-benefit analysis of the benefit you would get from that if you had those services, to be able to get more out of your wind and your solar. That 25 million or 235 million represents about 10 to 15% of the total energy or the total monies revenues that providing units can get, and moves it from ancillary services about 2% up to 10 to 15%. So it becomes a much more interesting payment, and it becomes a natural hedge for energy markets being more volatile and trending down in price in a world where we move from an operational cost model to a large-scale capital cost model. So in Ireland, we also recognise that because of our relative small size, we have to do it in a version of price regulation. If for a larger system, I would have a different view on that, and I can maybe have that discussion. But I acknowledge that this is price regulation, but I also acknowledge the transaction costs in Ireland of doing anything more than that will be prohibitive in my view. But the basic thing, in any product we have a tariff that it's put up there and they know they have it and they know it's likely that tariff for the next 4 or 5 years. And on top of that, we have scalers. The two that are really important is the performance scaler and the scarcity scaler. The performance scaler I'll talk about and the scarcity scaler, but a big thing, you can get multiples of your money or you can get less of your money depending on what you do in this space and when you provide that service, multiplied by the available volume. So that's the availability and the performance to meet performance scalers or scarcity are all within the control of the investor. So we're out of it. And that makes a very good thing. If they can be operating when we need them, and if they operate well consistently, they will be able to get a lot of money. If they don't operate consistently or they're not available to operate when they need to be operated, they won't get so much money. That's effectively the deal. On the performance reliability, we've effectively created a scenario that we say, look, if somebody's supposed to generate, say, 10 events a year of primary operating reserve, and there were 10 events, and in the 10 events they said they give me 100 megawatts of primary operating reserve, and in 10 events they gave me 100 megawatts 9 times out of 10. We're saying that's 100% payment, that's really good performance. If they were giving us less than 50%, 1 and 2 events, would you be prudent to schedule your system on somebody providing it when you knew that there were 1 and 2 events they mightn't provide it? So we just basically say you get no money below 50%. Now, what we have to do to make this happen, we have to measure performance on a regular basis, but we're basically monetizing performance metrics. So the performance of a providing unit for services is all within their gift to manage. Now, if they don't have an OEM contract backed off, or they only have an OEM contract with availability and efficiency, maybe they're not designed to deliver this performance, but I'm trying to get investment decisions made that people will actually back end off these type of performance metrics across the 14 products into OEM contracts. That's where we get meaningful performance capability and they get a reasonable return for doing it. So that's a key aspect of the design of this system service arrangements. We also are looking at scalers, scarcity scalers, and one of the obligations the regulators said on us was you can't give any more money. The money can only go for new stuff. Now, the problem with the money going for new stuff, we are very happy to say if an existing generator can operate and provide loads of services up to say we're operating the system for 90% SNSP, well, we think they provide great value. We're happy to pay them a lot of money for that, and we don't want to rule out it. However, we got to target the money in those, and below 50%, we're saying we didn't actually need to know anything. So I'm basically saying we've created a scarcity scaler on some of the products where below 50%, you get no money. So all the new products are no money below 50% SNSP, but they go up to multiples of 4.7 or 6.3 times. So for every hour we're operating in that zone, and you are on the system available for service provision, you will get maybe 5 to 6 times your rate in that. Given that we're connecting 4,000 megawatts of wind, we're probably got an obligation to be operating in those hours a quarter of the year or a third of the year. And basically out of that you can make a lot of money, but it's only going to the people who can operate in high renewable scenarios, and will only go to them provided their performance metric shows that they are regularly and reliably able to deliver the performance that they've contracted for. So that's effectively the design of the products. When you look at where our money's going across the services, and we're trying to be agnostic, so we did 2 scenarios. We said, look, we don't mind if the existing plant as a spectrum enhance their plant and say drop all their minimum loads on large CCGTs, which means I have enough space. I keep all my inertia, but I have enough space for all the wind to act. That's one action. That's the enhanced scenario. And then new providers, we get in lots of battery storage, demand-side management. And we're agnostic technically of which we were doing. We're trying to show where the money might go. And what you see is that with with the new providers, we get a lot of FF4, batteries and DSM providing it, and that's where a lot of our money would go. But in the enhanced providers, we might get a little bit more. It doesn't show huge there, but the synchronous inertial response, we're getting more of that. It's quite small on this one, but it's about 2-3 million difference, which might make the difference in an investment on an annual basis. When we look at it in technologies where it's going, what we see is in the new providers case, that's demand side management gets more, and non-sync technologies is basically batteries. In the enhanced base case, there's little enough difference between them on the existing plant formula, a small bit. And I talked about allowing for new technology. So the issue in allowing for new technology is, look, that if these are the regulated arrangements, it simply wouldn't be prudent today, if I'm not using any DSM for fast frequency response, to say I'm going to contract with 1,000 megawatts of DSM and run it tomorrow. Yet if I don't do something to try and break down the barriers to allow DSM in for fast frequency response, I may never get there. So what we've created is an arrangement that the existing providers can move straight over. New technology service providers that are proven can go straight into a competition and to get a service arrangement with us. But to the extent you're not proven or we don't know how to measure it, we basically do a small-scale qualification trial, which they can get paid for, to prove it at small scale, where we're not actually using it to run the power system. We're actually using the trial, 1, 2, 3 megawatts of this, to try and work out the barriers and break them down, and then they're proven. Now they qualify for a larger contract. And without that sort of process in place, we simply wouldn't be able to get new technologies into the system. We'd be just effectively trying to give money to the existing technologies to do stuff, which may not be the most efficient answer out. In fact, I'd say it isn't. So how does this apply to the USA? How it applies to the USA is that if you're fundamentally going to do a lot of renewables, I would argue your power system needs to consider these things at scale. Now, right now, this slide that I put up here is taken from Reinventing Fire from Amory Lovins, where he goes out to 2050 and he talks about the total energy need of the United States. But ultimately what he's saying, if the total energy need is coming from 40% coming from other renewables, including wind and solar, fundamentally the electricity system in that system will be doing up to 80-90% renewables, because remember there's transport and heat in this as well. So I'm basically saying if that type of ambition is needed in America, you're going to have to do some of the stuff that I think we're talking about here. From a European perspective, when I talked about how does Ireland relate to European thing, what we see is they've already set out a strategy that basically says that energy usage out to 2050 is flatlining. There's not that much more increase in energy. But electricity in that is doubling in use as electrification of heat and transport. So it's 19% in 2010, goes up to almost 40% in 2050. So electricity in the three-phase AC power system is the backbone of solving the energy trilemma in Europe to 2050. When you look at the electricity mix in that, in 2010 they had 18% of the electricity system in Europe coming from renewables. Now that was mainly hydro. And by 2050, they want to get between a minimum of 55% and a maximum of 42% and 97% coming from renewables. Now, I don't think they'll get 97% by 2050, but if I take 18% away from 55% and say, look, 18% is the hydro and everything above that is coming from wind or solar, I get 37% by 2050. So Europe at a minimum is trying to do 37% of its electricity from wind and solar by 2050. Ireland's doing that by 2020. And we've fundamentally seen things that at a system level we think are relevant, that are not being embedded in market thinking today, which means you cannot get the incentives or the investment in an efficient manner to deliver it. Worse still, you may actually undermine the resilience of the power system. And if you end up with blackouts, you will get the worst of all, you'll get a political dislocation, which will create massive uncertainty. That when you need large-scale capital investment, the cost of that capital will be extra high. So how it relates to Europe is, I think Ireland is the benchmark of what a market needs to consider going forward. To support that at a European level, a lot of my colleagues weren't agreeing with some of the figures, so I went off and got a study done, very similar, a high-level study done on the European model out to 2040 with up to 40% coming from the renewable stuff. And when I looked at the technical scarcity graphs that we got from them, and I compared them in shape and size and scale to the ones that we actually had for Ireland in 2020, we seen the broad same shapes. So in Ireland, we went further and did all the technical studies at a level, but I'm saying is my conjecture, if you do that analysis in America, and I believe there was a paper in 2013, that good paper from NREL, which looked at a lot of this stuff, and they were seeing some of this stuff, and I think if you do this high-level sum, you will see that you're going to be down inertia, you're going to be down reactive power, you're going to be increasing need for ramping. And the simple thing I'm saying is, where is your market incentives? Where are you breaking down those barriers to meet it? Which ultimately leads to limiting issues. And those limiting issues are, first of all, I believe that people have built energy markets around the concept that people want a commodity called energy. And I argue they don't. And the reason why we have energy markets actually dates back to 1896, when Samuel Insull, who was the then head of GE, said after the war of AC-DC was over and they decided they were building AC, the businessmen said, how are we going to charge for this? And Insull said, we'll have a unit price of electricity and a standing charge. And I would argue that's the same bill that everyone has today around the world. And unfortunately, the economists, when we said we'd have wholesale energy markets, then said we need a wholesale energy market as the answer for that, building on that flawed assumption, business assumption made in 1896. But I would argue most strenuously that the consumer doesn't want energy. The consumer wants to enjoy the use of electricity to live their lifestyle when they want to. That's a utility, not a commodity. And the one thing I would give Thomas Edison, when he heard of Samuel Insull's model, he said, but hold on, I'm selling light, and next year I'm going to have a more efficient light bulb. Meaning, in some way, the business model that he was coming up would not proffer for his utility of creating light. So fundamentally, I'm saying energy markets are not delivering what consumers want. But the difference between a consumer utility and energy markets, in my views, is a public good known as the resilience of the power system. We all benefit. It's non-excludable. I don't care who you are, but you benefit from it, or the power system. I can't stop you getting the benefit of a reliable power system. And it's non-rivalous. There's nothing to rival. There's no option, you consume it or it doesn't matter. So I'm saying it's the perfect definition of a public good. And really what I think the consumer utility is, energy markets plus a resilience market, but recognizing that's a public good, which gets you into how you design that, which I would argue system services in Ireland is a version of a public good design. Which means ultimately I think your markets going forward need to balance the financial change on one side, which is going from an operational cost model to a capital cost model by 2050, recognizing that the technical scarcities today will fundamentally change in the future. And in order to meet those, you need to build a market that breaks the bridge between the financial issues that are thing, and the technical scarcities. Now, that's in Europe is the target model is a good starting point, but it in itself is completely insufficient to meet it. Capacity may be part of that, but also system services in an investable way, not ancillary services, and make them investable against future complementary performance to help meet the policy objectives. That's effectively your market design. I can get into how you might do it, and on a larger system when the transaction costs are small, how you also might do it. I want to wrap up very quickly now just to talk about technology distribution as well and bring in another dimension, which ultimately is the Internet of Things. And when you get down to, while it took about 70 years for electrification to happen all across America, and this is typical across every country I've looked at, in recent years, when you look at the adoption, say, the cell phone and Internet, it only took about 10 years for full saturation. Now, when we get into demand behaviors in the home, right now, power systems worldwide have been developed, designed, and planned on a diversity from consumers. Now, if I start to get technologies that now coordinate that power system in a way, we are actually got a huge problem, because if it's coordinated in anything that isn't the needs of the system, we will get behaviors coordinated that don't meet the needs of the system, and ultimately will lead to an undermining of the principles on which the system was based. So I'll argue this, that right now the focus on energy is probably too much. So when you go into a home, this is a standard home, somebody gets in the morning, they might turn on the cooker for breakfast, they'll go in, they turn on a light in another room, they'll have an electric shower, they might then go down and have turn on the fridge, the shower goes off. Your standard Tesla meter that's in there, all it is two readings when you read it between, so you have no discrimination of actually what went on in that house. Even smart meters, even a smart meter that measures every 30 minutes, all it will do is, it has no discrimination below 30 minutes. So if I wanted to measure a 2-second response, smart meters can't measure it. So why is everyone saying smart meters is the answer to everything? Yes, when I go into the Googles and the Apples and the Amazons, they're basically, people are willingly putting in technologies that will actually know what the person did and know what devices are turning on or off. They also know the time. Now, if there's some fungible way I can trust that data, I have now a completely different model that I can now implement, which is based on utility, based on lifestyle, not based on energy. And I would argue that fundamentally where we are going forward in Ireland, where we're at the moment traditionally, is that most power systems are in the command and control philosophy. The TSO says to the generation what to do, and it's an energy market. The tech giants are going to roll out a range of capability, whether we like it or not, that will coordinate load within the next 10 years at scale. The problem is, without the proper incentives and without breaking down the barriers to make it happen, it will just be in a way that actually is damaging to the power system, because it wasn't designed for coordinated actions from the demand. It was designed for diverse actions from the demand. When a distribution and sensor operator connects 100,000 homes, they connect them on the basis that the line will, no one will all turn on every device in the home at the same time. But yet, if that happens, they're going to potentially blow the fuses. Where I think in airgrid in Ireland, where we've got this world, we're still telling the wind farms what to do, but we've created a structure recognizing that there's barriers there, but it's about lifestyle. The resilience of the power system is what the consumer actually wants. And we've broken down barriers to get there, and we're in this sort of DS3 land. But where I think the holy grail is and where we need to get to is incentivize and influence over in the right hand, where we are creating incentives without telling people what to do. They do it because they want to do it, and somebody has managed that for them. That's where I think it will go, and that's where I think if we can do that, then there's a massive amount of capability in there that will actually assist and facilitate rather than frustrate meeting ambitious renewable targets. Thank you.
Okay, Jono, thank you for a very challenging and thought-provoking presentation. I would encourage those of you who have questions to go ahead and put them in. We have one question so far from Michael Doring. I've seen a lot of questions about the availability of the slides and the audio. They'll be made available within a week after the webinar today, and Margaret will send out an email to the participants so that you'll know how to get them on the UVIG website. So, question from Michael for Jono is the role of local markets in providing these system services in the future. And if I understand the question correctly, I think he's talking about devices, technologies that Jono referred to that are in the distribution system that aren't talking every second or every minute to the control center, but maybe there's a distribution system aggregator that plays the role of the TSO, it's the DSO, and can bundle and aggregate and provide those services and maybe bid them into the markets. I don't know, what's your view of the ability to obtain?
Well, I actually think, maybe it's slightly radical, I fundamentally think that it's neither the TSO or the DSO. I think the people who will actually be able to get the behaviors in homes and that are already there, the Googles and the Apples. I use my own phone as an example. I decided with my wife we'd make Thursday night, we're quite busy, we don't talk much, we're working too hard, and we have 3 small kids. Make Thursday night a date night there for a while, and we were going to a pizza place near us, and the 3rd weekend I got into the car at whatever, 7 o'clock on the Thursday. He says, you are 5 minutes away from a pizza shop up the road. So I'm basically saying I've allowed that type of invasive technology in my home, and I want it. And I'm saying the TSO and the DSO simply, if you're in a world where we're telling you, don't turn on something because the system can't deal with it, we've lost. It's a broken model. I think everything I'm talking about system services in Ireland, we are trying to get that value down to residents. So but we haven't got all the business practices and processes in place. And as part of that, there's a legitimate question that the DSO needs to, look, this may not be useful on my power system and it may cause me problems. And I'm saying that's fine. But I would go counter on that and saying, look, Apple's getting in there, Nest are getting in there anyway. So they're going to coordinate load whether you like it or not. So if you're saying to me, don't coordinate it for system services reasons because it's damaging, I'm saying, if you don't know it's going to damage your system, I would say, let me do it. If you can show me it's damaging, I won't pay them for your service at a time where it causes you a problem. So therefore, I'm not incentivizing behavior, and I believe I can do that. So I do, in Europe, there's definitely a big argument between TSOs and DSOs, but in my head, there's really 3 roles that a TSO or like EirGrid plays at the moment. There is the asset ownership of the network and the network operation of the network that we own. We actually don't own a network, but most TSOs do. A distribution system operator owns network and operates it today as well. Where I really see the difference is in system architect. Somebody has to system architect the whole thing, right, to make sure it works top down and bottom up. And I think those system architects needs to be the market, needs to be the business processes. And I see Europe going to a regional operations center where they're trying to seize control across multiple member states. And in 10 years' time, I conjecture that they're going to put in a super rock in control over all of those other rocks. So TSOs and DSOs become operating agents to operate rules and do it well. But the people designing the incentives and the broad direction are the system architects. And I would argue a lot of what I'm talking about is a system architect role. I fully accept right now that there is a battle between TSOs and DSOs in Europe. And it's all about holding on to a patch that both believe is theirs. And I'm actually saying I think that ship's going to sail. And if you hold on to that, you'll be irrelevant in the future, both TSOs and DSOs.
Okay, thank you. Question about capacity, adequacy, capacity markets. How do you see the capacity markets changing in the high renewables scenario? And should renewables bid into the capacity market? Should they be assigned to capacity? How do you see them playing? And I would add to that question also, how do you see the conventional players reacting as they see the capacity payments decreasing in the market design of the future?
Well, 3 things. First of all, capacity, I think, is something that's been overrated more generally. It's because we've had energy markets and capacity markets, and we've tried to put in value in there when we saw missing money in the energy markets and without really thinking about it. But I do accept as a system operator, capacity is an important consideration both now and into the future. So I see it as a system services, actually. I see that fundamentally, absolutely renewables and any source provider who can provide what is required should be included in those markets. Now, the question is what is required, and that's where I say, look, part of our thing is ramping. It's a ramping product, which it's what's the risk I have in 1 hour? Could you provide me a margin of comfort if you were there in an hour? And maybe wind can do that if they're part loaded. Wind can actually do that in part loaded. Actually, wind is one of the best technologies I've ever seen on the power system, provided you don't run on a full load. If I run on a full load, I basically have a situation where I have to manage the variance of wind. Now, I come to, Charlie, the third part of that, saying capacity in Ireland is already being reduced. And what we see in the behaviours with other incentives, conventional plants are trying to change their performance to get at these monies for, say, synchronous inertial response, to be able to operate in a world with high renewables, with low energy output, but with lots of service provision. So in my world, we currently have an 8-set minimum rule on the Ireland system today, but each of the sets only have a minimum, the large sets have a minimum of, say, 200 megawatts. That means I have 1,600 megawatts of fossil fuel synchronous generation always on my power system, which means there's less space for renewables if I want to get higher targets. Now, I'm happy to pay for those 8 sets of generators to sit at 0 megawatts, still spinning and providing all their inertia and all of that, and make that 1,600. I'm just saying the energy market at the moment doesn't reward for it. But I'm saying what we have seen by doing system services is that generators that previously said they couldn't do something, miraculously were able to do it once the incentive became clear. And there's a double incentive. They're not going to make their money in a market where previously they had 100% of the market and the government said, we want 40% of that market to go to renewables. So that's something outside my control. Somebody has to lose in that world. And that's a policymaker's decision outside my, that should be allowed to happen, and that's sort of tough. Lobby the policymakers, as everyone sort of does, and that's the renewables and the fossil fuels. But what I think they do see is some of the people who are on the margin of that equation, seeing that they can't make their money in energy but have already made an investment, are seeing that they might be able to get better performance out of their CCGT and make some good money in system services, which means they're still making they're still getting a return for their investment. And we've seen a lot of that since these incentives have been discussed.
Okay, I want to ask you a question, John. If somebody's curious about how the wind plants performed during Hurricane Ophelia.
What I can't say, or I can talk about Storm Darwin, because I haven't actually, all non-essential, and I wasn't operational yesterday. I wasn't in the control center, and in fairness, I haven't gone near it, because when you're in crisis situations, just leave them alone. But I can talk about Storm Darwin, which was a similar outcome about 3 years ago, which we weren't prepared for. So my understanding yesterday, with Storm Ophelia coming in, we basically, a Hurricane Ophelia, we basically brought on a lot of conventional plants, started curtailing the wind because we were worried about high-speed shutdown. And we know by our own analysis that above 25 meters per second, so above 90 kilometers per hour, you are going to lose half the wind fleet on high-speed shutdown. So we basically wanted to manage that. So I think we managed it easily yesterday, no problem. Storm Darwin was probably a better challenge, where it was 3 years ago, where we weren't expecting, but Hurricane Ophelia, we lost 350,000 customers. Storm Darwin, we lost 320,000 customers. We weren't ready for it. We didn't think it was a big storm, and it was, and we lost wooden pole. In that one, we were up at 45% of the system coming from wind, over an hour because of wind lines being blown out and high-speed shutdown. We lost about 1,000 megawatts of wind. We lost 320,000 customers, but we didn't lose the system. So I think it's an absolute testament to the policies and principles of the DS3 program that in the biggest storm at that point in time that came onto the Ireland power system, it passed with flying colours. We were an organisation in 2002 said we couldn't manage more than 400 megawatts of wind. So 10 years later, we're up at 2,500 megawatts, up to just under 50%, and the system sailed through on resilience, no hassle. And so yesterday, I think we even managed it all. That risk was even better managed because we knew the Hurricane Ophelia was coming in.
It shows you what you can do when you put your mind to it.
Correct.
We're about at the top of the hour here. I told you that we would try to wrap it up. Now we've got some more questions, but hopefully we can take those offline if people would like to pursue them. I want to really thank Jono for a very thought-provoking and informative discussion and presentation. As I said, the link will go out with the file and the audio in it for all those participating. Really appreciate your engagement. Look forward to seeing you at our next webinar, which is going to be held in conjunction with NERC on Monday, November 6th, following up on some of the essential reliability services discussions, which tie right into Jono's discussions here today, services. And I want to thank you all for your participation and look forward to seeing you the next time. And Jono, thank you.
Thank you.